In this part of the course, we're going to cover the basic concepts and systems involved in broadband RF distribution in and to the home.
Now we're going to cover the distribution of external signals, such as cable, satellite, and off-air signals, the distribution of internal sources, such as DVD players, modulated AV sources, cameras and computers, coaxial cable types and their characteristics, direct broadcast satellite systems, off-air antenna systems, and the details of active and passive distribution system components.
Throughout this course, we'll use the term broadband RF to mean systems and services like cable television, where the cables support a number of channels or carriers simultaneously. This typically implies RF signals from several megahertz through the gigahertz frequency range. The term video will be used to mean a baseband video signal. The signal typically available at the video output jack of a VCR, DVD player, or the signal from a security camera. A broadband distribution system must support the distribution throughout the home of external sources such as cable service signals, off-air signals, and satellite signals.
It must also support the distribution of in-home generated sources such as VCRs, DVDs, and other entertainment program sources, cameras, and computer-generated media. Let's start with the technical requirements for each external source, starting with traditional cable service. In this section, we're going to cover what you need to know to integrate cable television signals into your distribution system. The majority of cable industry distribution systems are based on a hybrid fiber coax architecture. Fiber optic backbone cables carry signals to coax distribution point locations in a neighborhood. From there, underground or overhead coaxial cables carry the signals directly past individual homes or apartments. Service is supplied to individual homes from tap points on the overhead or underground coaxial cable runs through a drop cable to the customer demarcation point. The cable television industry uses a standard channelized frequency allocation on their distribution system. Downstream channels start at channel 2 and go up beyond channel 125. You've got a copy of this table in your workbook, so look at it. The table gives the channel allocation frequency and visual carrier frequency for each channel for 3 band plans, the EIA standard plan and the older IRC and HRC plan. Cable companies were required to begin using the EIA standard frequencies prior to 2000. Most cable companies also use the spectrum below channel 2 for upstream or reverse channel services from the home back to the cable plant. These channels are designated T7 through T14 and were originally used for transmitting channels from outlying offices or studios back to the head end. Now they're used for a variety of services, such as the upstream data from cable modems, pay-per-view signals from set-top boxes, and so on. Most cable services nowadays utilize up to channel 62, with newer systems using channels up to the mid-80s. This diagram illustrates the spectrum used by a typical North American analog NTSC television channel. Channels are 6 MHz wide, the channel width established for off-air TV broadcasters by the FCC. Cable companies carry these signals exactly as they would be broadcast from an off-air station. An NTSC television signal is actually made up of 3 separate signals combined into one channel. A video carrier 1.25 MHz above the lower edge of the channel. This carries the brightness or luminance information in the picture and defines the detail in the picture. A color or chrominance carrier 3.58 MHz above the video carrier that defines the hue and saturation of the picture. And an FM monaural or stereo audio carrier 4.5 MHz above the video carrier. Now, this diagram shows the frequencies of the signal as if it were broadcast on channel 2. For any other channel, just add the starting frequency of the channel.
This spectrum analyzer is an excellent tool for visualizing what cable, antenna, or other RF signals look like. It shows a graphical display of amplitude versus frequency. We'll use this tool a lot to show what various RF signals look like. We have connected directly to the local cable service so we can take a look at some of the signals on the cable.
The display is set to show the entire spectrum transmitted by the cable operator, starting at channel 2 up to channel 116. Now, the lower part shows the analog channels, and this upper part is all the digital channels. Now this is what a series of the analog channels look like, each occupying a 6 MHz bandwidth. This is a zoom in on a single channel. You can clearly see the video, color, and audio carriers within the 6 MHz channel bandwidth.
You know, Grayson, the cable companies use 6 MHz channel spacing to transmit other things as well, such as test and maintenance, or digital content, such as digital data services or digital television.
Right. Now the term digital cable or digital cable channel refers to the content, not the type of channel.
Exactly. Every signal on cable is analog. It's either traditional analog television or digital content on a carrier modulated with the data services such as a modem or digital television.
Right. By using sophisticated compression techniques, cable companies can squeeze 6, 8, or more digitized NTSC channels into a single 6 MHz space, greatly expanding their channel capacity.
Exactly. But this requires a digital set-top box that will convert the signals back into the NTSC analog.
This display shows a series of digital channels, each 6 MHz wide, starting at channel 80. This is a close-up of channel 92. Now, while it just looks like noise to us, it actually contains 6 MPEG-encoded digital channels. A digital cable modem channel looks exactly the same. The amplitude of cable signals, and all the RF signals we'll be using, are expressed in decibels or dBs. You'll need to have a good understanding of dB units and how they're used.
Exactly. The dB is a simple way of expressing the ratio of two different values, such as power or voltage.
Right.
They are used to simplify calculating the gains and losses in RF systems or components.
For example, if we know the signal into an RF amplifier is 1 volt and the output is 2 volts, we know by this formula that the amplifier has a plus 6 dB gain. Likewise, if we know the signal into a length of coax cable is 1 volt and the output at the other end is 0.3 volts, we know the coax has a loss at the frequency of the signal of minus 9.5 dB. By convention, the minus sign means a loss. This is a table of common signal level dB gains and losses. Notice that increments of 20 dB voltage gain or loss is equivalent to powers of 10 increase or decrease. Plus 20 dB is equal to a 10 times increase. Plus 40 is equal to 100 times, and so on.
Fortunately, when designing an RF distribution system, the dB gain or loss of a particular component, like an amplifier or the coaxial cable, is given to you by the manufacturer. So all you need to do is add them together for each path through the system. For example, if we know that the loss of a brand of coax cable is 8 dB per 100 feet, then this system, with 100 feet from the cable service NID to an amplifier, with 10 dB of gain, then another 50-foot length of coax to a TV, will have an overall gain or loss of minus 8 and plus 10 and minus 4, or a total of minus 2 dB of loss. So if we know the input signal level, we can easily figure the output signal level.
While dBs express a ratio, absolute cable company signal levels are typically given in a unit of measure called a dBmV, or decibel millivolt. The MV after the dB means an absolute signal level reference to 0 dBmV. 0 dBmV is a standard reference level of 1 millivolt of the visual signal level across a 75 ohm resistance. 75 ohms because the cable system is built around 75 ohm impedance cables and equipment. A 3 dBmV signal has a level of 1.41 millivolts across a 75 ohm load, and a 10 dBmV signal has a level of 3.2 volts. Likewise, a minus 6 dBmV signal has a level of 0.5 millivolts. A minus 3 dBmV signal applied to an amplifier with a 10 dB gain would result in an output signal level of plus 7 dBmV. We'll talk more about amplifiers and amplifier gain shortly.
The FCC regulations that govern cable systems, including the part of the customer system that you're installing, are covered in FCC Part 76. It outlines all of the rules and regulations that cable system operators and you must adhere to.
Now, among other things, it defines various signal levels that are applicable to residential distribution systems. Your workbook has got a list of some of the most important signal level parameters.
The cable company's visual signal level at the NID or connection point at the house should not be anything less than plus 3 dB MV on any channel.
This assumes a 100-foot cable run from the subscriber tap point of the cable system to the house. Now, the signal level in the house at the point of connection of the customer's equipment should not be less than 0 dBmV on any channel. Now, the only upper limit given in Part 76 is, I quote, a maximum signal level such that signal degradation due to overload of the subscriber's receiver does not occur, or something like that. Now, that's usually a maximum of plus 15 dBmV, and ideally in the range of 0 to plus 10 dBmV. This is also the range that the cable tuners in televisions are designed to handle. When the signal level drops below minus 10 dBmV on a particular channel, the picture will begin to show noise in the picture, commonly referred to as snow. This is minus 15 dBmV, minus 20 dBmV, and minus 25 dBmV. Not so good. When the signal level exceeds plus 15 dBmV, the picture will begin to exhibit a noisy herringbone pattern, an indication of tuner overload. This is plus 25 dBmV and plus 30 dBmV. Part 76 also says that the difference between any two adjacent channels should not exceed 3 dB, and no more than 10 dB difference between the lowest and highest level of any channels. The regulation also specifies a minimum 43 dB carrier-to-noise ratio at the outlet. This means that any noise present on a channel must be at least 43 dB below the amplitude of the visual carrier. Another attribute that Part 76 defines is the hum modulation level on a video signal. This is where a 60 or 120 cycle voltage, typically caused by a bad amplifier power supply or improper grounding, gets added to the video signal. Hum will show up as visible white, gray, or black bars slowly rolling through the picture. The intensity of the bars depends on the amplitude or percent of the hum modulation on the signal. Hum levels should never exceed 3% of the signal level, or it'll definitely become visible.
RF signals can be easily measured utilizing a portable signal level meter like this. This unit will make any number of key measurements on any cable signal or off-air signal with an input range of minus 35 to plus 60 dBmV. It will measure RF and AF carrier amplitudes, carrier-to-noise ratios, hum levels, and so on. We'll talk more about working with cable service providers to ensure a successful install in Part 2. Next, let's look at some of the characteristics of coaxial cable in more detail.
Now, since everything RF is interconnected with coaxial cable, you're going to need a good working knowledge of its characteristics, especially loss performance, to design and install RF systems. Now, we've covered coaxial cable types and their characteristics in detail in our other courses. So we're only going to review issues that deal with loss and signal ingress and egress. By far the most common coax cable for residential use, recommended by TIA 570, is Series 6. The most common designation for Series 6 cable is RG6. RG6 offers a good combination of size, cost, and low-loss performance for the distances typically found in homes, and it'll be your cable of choice for residential installations. This chart, also in your workbook, gives typical loss figures for RG6 for 100 feet at frequencies up to 1000 megahertz. Remember, loss is frequency dependent, increasing with increasing frequency. It's also additive. 200 feet has twice the loss of 100 feet, 50 feet has half the loss, and so on. The loss in coax is a function of the materials and dimensions of the coax, the biggest contributor being the dielectric insulating material. While the best insulation is a vacuum, it's not very practical. Foamed or cellular dielectrics are the most popular. In general, the larger the diameter of the dielectric, the lower the loss. At 700 MHz, RG59 with a typical diameter of 0.2 inch has a loss of 7 dB per 100 feet. RG6 with a typical diameter of 0.27 inch has a loss of 5 dB. And RG11 with a typical diameter of 0.4 inch has a loss of only 3.5 dB. Beside loss, the other most important characteristics of coax cable is its resistance to signal ingress and egress. Of the two, the most important is signal ingress, outside signals getting into the cable.
Exactly. Ingress can be a real problem when there's a lot of high-powered FM stations, local TV channels, and amateur radio bands, which can cause, problems with cable or modulated channels.
Right. Now, defending against signal ingress is the job of the coax shields.
Shields come in two varieties. Foil, where aluminum is bonded to both sides of a plastic tape to provide 100% coverage, and the braid, where flexible wire is woven around the dielectric. Braid coverage is usually less than 85%. The foil provides 99% of the ingress protection, while the braid is used primarily for strength to prevent breakage of the fragile foil.
You can purchase RG6 with one braid shield, a foil and braid, a foil braid foil, and a quad shield, foil braid foil braid. For maximum ingress protection, make sure you use either tri or quad shield RG6. And check the quality of the shields of the cable. There's a big difference in shield types and coverage between manufacturers. Another important specification is the DC resistance of the center conductor and shield. Very important when the cable is used to supply power to attached devices such as cameras and satellite antennas. This chart shows the typical DC resistance of the center conductor and shield for a quad shield RG6 and the total loop resistance per 100 feet. Notice the big difference between solid copper and copper-clad steel center conductors. This is the reason that solid copper should be used when you supply power over the coax. There are an ever-increasing number of F connectors available for coax cable. Just make sure you use a high-quality connector that forms a tight seal with the jacket and the shield. Most RF-related service calls are a result of poor F connector installation. The most common one-piece connectors are the hex crimp and compression crimp. These incorporate an integral crimp ring for strength and ease of installation. The most common two-piece is the snap and seal connector, applied with a special tool. Newer versions of this connector have the plastic sealing ring already in position on the barrel. F connectors are available for 2 and 3 shield RG6 and for quad shield RG6. Make sure you use weather-resistant F connectors outside. They have a built-in O-ring seal, and the crimp barrel has a dielectric silicon compound pre-applied to keep the moisture out of the coax. We also recommend using a weather boot. This keeps moisture and UV off the entire connection. You just have to remember to put it on the coax before you apply the connector. Improper coax and F connector installation is also the leading cause of signal egress from the home. Now, the FCC establishes strict signal egress limits on the cable industry to prevent cable signal interference to other services, especially aircraft navigation. Now, if your installation has found a leak, the cable operator will disconnect service and not reconnect it until you can show that the source of leakage has been found and corrected. So make sure you get it right the first time. This is Channel 9's transmitting tower up here. They put out 10 kW into that.
Off-air signals originate at privately licensed transmitting towers such as these on a mountaintop north of Tucson, Arizona.
Now, this particular tower is the station's main VHF transmitting antenna, outputting over 100,000 watts effective radiated power.
It also contains a newly installed UHF antenna. We'll talk more about that shortly.
The antennas are designed to concentrate the power in the direction of the major population area to the south. Since both VHF and UHF signals operate line of sight, they're limited by the curvature of the Earth. A typical 1,000-foot transmitting antenna only has a range of about 40 miles.
That's why broadcasters try to get their antennas as high as possible, and the reason you want to get the receiving antenna as high as possible as well.
Now, these broadcasters were lucky. They just happened to have an 8,000-foot mountain handy next to their major market, so they only have to be a couple of 100 feet high.
They've got a line of sight of over 100 miles. You know, Grayson, there are many good reasons to incorporate off-air broadcasts in your RF distribution system. First, and maybe most important, it's free.
A major plus. Or when local stations aren't carried by the satellite providers, there is no cable service, or most recently, to receive new digital television signals.
See, nearly all broadcast stations must deliver digital television, or DTV, by 2006, and most have already started. With a good antenna installation, there's no reason why the picture quality from off-air can't be just as good as the picture from cable or even satellite.
It's a good alternative to cable and satellite as the sole source of television reception, and as Frank said, it's free. This chart, similar to the one we saw for cable channels, shows the UHF and VHF frequencies for each 6 MHz TV channel. Notice that the VHF channels are divided into two groups, channels 2 through 6 and 7 to 13, sometimes referred to as the low and high VHF bands, at 54 to 86 and 174 to 216 MHz respectively. Between these bands lie a number of other radio services, such as FM stations between 88 and 108, and aviation band between 108 and 136 MHz. UHF channels 14 through 69 occupy channel frequencies from 470 to 890 MHz. Since off-air and cable channels above channel 13 use different frequencies, television or other receivers have to have tuning modes that select between cable or off-air frequencies. To implement the transition to digital television, the FCC granted each existing broadcaster an additional 6 MHz UHF channel to be used exclusively for digital transmissions.
That's why new UHF transmitting antennas have been added to these TV towers. Broadcasters are free to broadcast either standard definition, enhanced definition, or high definition digital signals.
At the end of the transition period, sometime after 2006, the existing VHF channels are going to be reallocated to new services.
Broadcast television signals, whether analog or digital, need to be captured by an antenna designed specifically for the VHF or UHF frequency range.
And since you've got to be familiar with specifying and installing off-air antennas, we need to spend a little time understanding how they work.
Exactly.
Antennas are the closest thing to magic that you'll ever encounter. And TV antennas work just like all antennas, by capturing a very small amount of the arriving electromagnetic field transmitted by the broadcast antenna that just happens to arrive at the receiving antenna location. Now, the arriving field will cause electrons in the metal elements of the antenna to vibrate very small amount at the transmitter frequency. This generates a small voltage between 100 and 1,000 microvolts at the antenna terminals. This is carried by the connecting cable down to the receiving equipment. Now, no one has ever seen an electromagnetic field. I once knew a guy in the Army claims he could, and maybe he could. But he's been in long-term psychiatric care so long, nobody cares. Now, how well an antenna works is determined primarily by the amount of exposed metal elements to the arriving electromagnetic field. In general, the more area, the better. But antennas are typically designed so that the receiving elements are at least a half wavelength at the lowest operating frequency. At the low end of the VHF channels, this turns out to be 9 feet, and the upper end of the UHF channels, this is only 7 inches. So most antennas are designed to be a compromise between the two. Now, there are a couple of myths about antennas that we need to dispel right away. First, that you need some kind of special antenna to receive digital broadcasts or digital TV. In fact, all broadcasts are analog signals. The DTV refers to the information or the content of the broadcast signal, or the broadcast carrier as it's called. All broadcast signals are the same, and any antenna is perfectly capable of receiving traditional analog or digital broadcasts. Now, broadcasting digital content does have certain advantages and can influence the selection of an antenna, and we'll talk more about that in part 2. Now, the other myth is that antennas somehow pull in RF signals. In fact, TV antennas no more pull in RF signals than my eyes pull in light from the sun. Antennas are in fact passive devices. They'll only receive electromagnetic signals that arrive at the antenna. If it doesn't get here, we don't pick it up. However, antennas such as this can be designed to favor signals from a particular direction, sort of like me holding up a tube to my eye to favor light from a particular direction. However, I suppose you could say that the design elements of the antenna create a quantum probability field around the antenna that significantly raises the probability of the occurrence of electromagnetic quanta with the energy level of the design frequency of the antenna, but we're not. One of the biggest problems you'll need to deal with when using an off-air antenna is multipath reception. The signals transmitted from a broadcast antenna travel in a direct line of sight to the receiving antenna. However, signals from a broadcast antenna can be reflected from nearby objects such as buildings or mountains and also arrive at the receiving antenna slightly delayed, like an echo, usually at a lower signal strength. Several reflected signals can arrive from different paths, each delayed a different amount depending on how far away the reflecting object is. The echo signals show up as ghost-like images to the right of the directly received signal. There are several ghost images in this picture indicating several multipath signals. The delay or displacement of the ghost indicates the relative distance from the receiving antenna of the reflecting object. Multipath signals can be a problem at VHF frequencies, but the effect gets worse as the frequency increases, since smaller and smaller objects become more reflective. At high UHF frequencies, it becomes a major problem. Multipath signals can also occur from ground reflections from the transmitter to the receiving antenna. Now, depending on the path difference of the reflected signal, it can either attenuate or enhance the signal by as much as 6 dB. Therefore, it's a good idea to test the antenna at different heights for best signal if possible. Moving the antenna up or down a few feet can make a big difference.
Now, antennas are designed around two criteria: the frequency range they cover and their directivity.
Antennas can be designed to receive a narrow range of frequencies, such as a single or small group of VHF or UHF channels, or a broad range of channels, such as the entire VHF or UHF band.
Now, VHF antennas such as this are designed to cover the two VHF bands as well as the FM band. They have longer elements due to the lower frequencies of those bands. This UHF-only antenna is designed to cover the broad spectrum of the UHF channels. It uses elements which are much smaller due to the very high frequencies of those bands. Now, some manufacturers combine the two into one design, such as this combination VHF and UHF antenna, which also covers the FM band.
The best combination is a dedicated VHF antenna and a separate dedicated UHF antenna, such as this. Each antenna can be optimized for the respective band with minimum interference between them. Then they can be mounted on the same mast and pointed in different directions if necessary.
Now, the other design criteria is directivity. Antennas are either non-directional or omnidirectional as it's called, or directive. An omnidirectional antenna is designed to receive frequencies in all directions.
Manufacturers make a variety of omnidirectional antennas for TV reception, typically by combining bidirectional elements or shaping the elements, such as this.
Omnidirectional antennas such as this should only be used in areas of flat terrain, void of any tall structures that would cause a problem with reflected or multipath signals, and where the signal strength of the desired channels are adequate. Now, directional antennas fall into two categories: bidirectional and unidirectional. Now, the best and simplest example of a bidirectional antenna is this dipole antenna, as it's called. It receives equally well from two opposite directions. It's a single element about 1/2 wavelength connected in the center with the connecting cable. Now, this omnidirectional antenna is actually two bidirectional dipole antennas connected perpendicular to each other.
Several styles of simple bidirectional antennas are available for attic as well as roof mounting.
Bidirectional antennas are best used in suburban areas where all of the transmitters are either in one direction or in opposite directions, and there are few tall structures or mountains in the area.
This antenna pattern, as it's called, is drawn looking down on the antenna from above and shows its relative directivity or sensitivity to receive signals in a 360-degree pattern. Now, this is the pattern of a bidirectional antenna. While some side rejection is available, the pattern's very wide and multipath reception can be a problem.
By adding extra elements to a dipole antenna parallel to the dipole, the antenna can be made directive so that it receives signals from only one direction, or said another way, that it rejects signals from all but one direction. Now, these multi-element antennas are referred to as Yagi-Udas, believe it or not, based on the two guys that invented the thing, or just Yagis for short. Now, the size and the placement of the elements is designed to receive and reflect the signal back to the receiving element at precisely the right phase to enhance the signals from one direction and attenuate the signals from all other directions.
This unidirectional antenna pattern shows its one-sided sensitivity as compared to the bidirectional antenna. To cover the entire range of frequencies in the VHF or UHF bands, most manufacturers use a series of receiving dipoles of different lengths in this characteristic V shape. These are called log-periodic antennas. The dipole elements are crisscross connected together. In general, the more elements, the greater the antenna directivity, and the greater the antenna is able to reject multipath signals. Directivity is also expressed as the antenna gain. Antenna gain is a ratio, expressed in dB, of the received signal strength of an antenna in its most favorable direction compared to a reference antenna, typically a dipole, in the same direction. Gain is also an indicator of the directivity of an antenna in the most favorable direction versus the side or rear of the antenna. An antenna with a high gain indicates high directivity. For example, an antenna with 6 dB of gain over a dipole will output a signal voltage to the receiving device that's twice as large as the dipole antenna in the same location receiving the same signal. Antenna manufacturers will also express the gain as a recommended maximum distance from the broadcast antenna, such as 25 miles or 50 miles. They assume a typical transmitter radiated power, usually 100,000 watts, and calculate the maximum unobstructed distance that will output at least a minus 10 dBmV signal from the antenna with the antenna pointed directly at the transmitter.
This is a good example of a medium-range combination unidirectional antenna. The large elements in the rear are optimized for VHF frequencies, and the small elements in the front are optimized for the UHF frequencies. Now, since UHF frequencies are so prone to reflections, the UHF portion of the antenna has additional elements to increase the off-angle and rear rejection of UHF frequencies.
Raking the VHF elements forward is very common for both Yagi and log-periodic antennas. It's an engineering trick that allows fewer elements to be used over a broader range of frequencies.
Now, unidirectional Yagi antennas like this are definitely the antenna of choice in areas like this where there are high mountains or tall structures. This area would be a multipath nightmare. Now, it's also not intuitively obvious at all which way you point these antennas. You might think from the way these elements are mounted that you'd point the antenna in this direction. In fact, the only reliable rule of thumb is that the larger elements, called the reflectors, are in the back, and the smaller elements, called the directors, are in the direction that you want to point the antenna.
In the UHF band, where elements are small, these reflector antennas are excellent at reducing multipath signals from the back and sides of the antenna. While many amplified antennas are available, they shouldn't be needed if you're connecting an antenna to a distribution amplifier.
Since FM radio represents an excellent source of music as well as news, FM signals should be integrated with TV off-air signals for distribution. And an outside FM antenna is essential for a good signal-to-noise performance.
The FM band is from 88 to 108 MHz, right in between VHF television channels 6 and 7. FM stations are assigned center frequencies at 200 kHz separation, starting at 88.1 MHz for a maximum of 100 stations in any area. An FM stereo station occupies up to 150 kHz of bandwidth, leaving 50 kHz between each station as a guard band. FM signal levels at an antenna are usually much lower than TV signals. FM receivers are more sensitive, typically requiring less than 10 microvolts for full quieting reception, 100 times less than a video signal. However, FM receiver performance varies drastically, and price is not an indicator of better performance. We recommend using a dedicated FM tuner that has a full quieting sensitivity spec of not more than 5 microvolts.
While broadband VHF antennas can certainly receive FM signals, using a separate outdoor FM antenna is a good idea for a couple of reasons. First, FM stations tend to be scattered geographically over a wide area, rather than clustered together like TV stations. And secondly, high gain's usually not necessary for FM stations in a 40-mile radius, and using a highly directive TV antenna may actually be a disadvantage. and FM signals are not nearly as susceptible to multipath interference as TV signals are. This omnidirectional antenna we saw earlier is a good choice for local stations that are located all around like they are here in Tucson. But to receive stations from a nearby town such as Phoenix, a Yagi antenna designed for the FM band is a good choice. It's got enough gain in one direction, yet can receive local stations from most other directions. Historically, off-air antennas are designed to use this older twin-lead cable. Despite its appearance, it's actually a very good low-loss cable. The trouble is you've got to keep it away from metal objects and other cables, and it's susceptible to noise pickup. A better choice is to use RG6 coax. Now, the characteristic impedance of RG6 is 75 ohms, while antennas are designed to use the 300 ohm impedance of twin lead. Therefore, in order to connect coax to the antenna, you'll need to install a 300 ohm to 75 ohm impedance transformer such as this balun. Now, we're going to cover more about the selection and installation of off-air antennas in part 2 of the course. In this part of the course, we're going to cover direct broadcast satellite systems. Now, these systems are also referred to technically as Ku-band DBS systems, due to the designation of the 12 gigahertz downlink spectrum it uses as the K sub U or Ku microwave band. Introduced by RCA and Hughes in the early 1990s, it's by far the most popular satellite technology ever invented.
Source television signals are converted to a digitally compressed MPEG-2 data stream. The data stream is transmitted on a 17 gigahertz uplink carrier to a geostationary satellite. In the satellite, the received signal is converted in a device called a transponder to a 12 gigahertz downlink carrier and broadcast over a wide geographic area visible by the satellite. The signal is received by a small high-gain dish antenna pointed at the satellite and connected to a specialized receiver. The receiver converts the signal from an MPEG-2 data stream back to the original analog form for viewing on a local television. The satellites are 22,300 miles from the Earth's surface in an orbit around the equator. This region is known as the Clark Belt, after Arthur C. Clarke, who in 1945 worked out that an object at this distance in space would appear motionless from the Earth's surface. It moves around the Earth exactly in sync with the Earth's rotation, hence the term geostationary orbit. The U.S. has allocated 8 orbital positions, 9 degrees apart, roughly centered over North America, for high-powered direct broadcast service. The most desirable positions are 101, 110, and 119 degrees, since from these locations the satellites can cover the entire U.S. The 101 degree position corresponds to a north-south line passing through western Nebraska. Using this line as a reference, the satellites appear due south when viewed from central U.S., west of south on the east coast, and east of south on the west coast. Each orbital position can have a maximum of 32 transponders, possibly divided between several satellites at that position. Each transponder receives an uplink signal in the 17 gigahertz band and transmits a 24 megahertz wide downlink signal between 12.2 and 12.7 gigahertz, a 500 megahertz bandwidth. To squeeze 32 transponder signals at 24 megahertz each into a 500 megahertz bandwidth, that works out to 770 megahertz, the system uses a clever engineering trick. Odd-numbered transponders use a downlink antenna with right-hand circular polarization. The antenna looks like a corkscrew to the right, literally spinning the electric and magnetic field clockwise. Even-numbered transponders use an opposite corkscrew antenna to the left, spinning the electric and magnetic field counterclockwise. The receiving system has 2 separate antenna elements that are highly sensitive to the polarization. While this adds to the complexity of the system, using circular polarization allows overlapping the transponder channel frequencies to cram more into the 500 MHz downlink bandwidth. Each transponder's 24 MHz bandwidth can support a 40 megabit per second data stream divided between 1 to 11 MPEG encoded channels. Now this gives an average of a 256 channel capacity for the 32 transponders at each orbital position.
Satellite service in the U.S. seems to be constantly changing, but at the time we made this course, there were 2 major suppliers of DBS service: DirecTV, owned by Hughes, and the Dish Network, owned by EchoStar. DirecTV was co-developed by Thomson Consumer Electronics RCA brand and Hughes. DirecTV has a license for all 32 transponders divided between the 3 satellites at the 101-degree position. The 3 satellites are so close together in space that a standard 18-inch DirecTV dish doesn't have to move to pick up the signals from all 3 satellites. DirecTV also operates 3 transponders on a satellite at the 110 position and 11 transponders on satellites at the 119 position. Now, receiving from 3 separate orbital positions means using a new antenna with 2 additional LNBs and a larger dish. We'll talk more about that shortly. The dish network operates 24 transponders from an EchoStar satellite at the 110-degree position and 16 transponders from satellites at the 119-degree position. They also have transponders at 61.5 and 148-degree positions. These provide additional local network and high-definition programming. The satellite at 61 degrees is intended for receivers on the East Coast, and the satellite at 148 for receivers on the West Coast. This gives each provider access to over 350 channels. Because of the very small wavelength of Ku-band satellite signals, a half wavelength is only a ½ inch. Satellite antennas can achieve very high gain in a very small space. This 18-inch parabolic dish is typical of direct broadcast satellite receiving antennas. It has a typical gain of about 34 dB, equivalent to a gain of over 2,000. Compare that with the 6 or 10 dB of a typical off-air antenna. Now, every bit of that gain is needed because the arriving satellite signal is extremely weak. Imagine trying to see a 100-watt light bulb at a distance of 22,000 miles, and it'll give you a little idea of the problem. Now, arriving signals from the satellite are reflected like light from the parabolic dish to its focal point at the open business end of the antenna, the low noise block converter, or LNB. Now, it's this focusing action of the dish that gives this antenna such a high gain. The LNB contains a tiny pair of antennas inside this feed horn where the signals are focused. The antennas are connected directly to a pair of high-gain, low-noise amplifiers on the LNB circuit board. Now, depending on which polarity is selected by the receiver, the odd or even amplified 12.2 to 12.7 GHz signal is then block converted, mixed with an oscillator signal at 10.75 GHz, to produce an output range of frequencies from 950 to 1450 MHz. Now, the block conversion is done here at the satellite antenna so that you can use a relatively inexpensive cable, such as RG6 or RG11, to feed the signal down to the receiver at a frequency that produces a relatively low loss in the cable. Now, you could, however, take the 12.2 GHz signal and feed it right down to the receiver and do the block conversion there. But in order to do that, you'd have to use something like this microwave hardline at $10 a foot to do the job. Really cool cable, and this produces a really nice installation, but we don't recommend it. Now, power for the LNB is supplied by the receiver over the same coaxial cable used to feed the LNB output down to the receiver. The receiver uses the center conductor and the shield of the cable, positive on the center conductor, ground on the shield. Now, the voltage that it puts on the cable is used to select the even or odd channels out of the LNB. 13 volts will select the right-hand polarized odd channels. 18 volts is used to select the left-hand polarized even channels. Whichever channel is selected by the viewer determines the voltage the receiver outputs to select the appropriate transponder channel. The geometry of the dish reflector and the position of the LNB means that each LNB can only see one orbital position. To receive broadcasts from additional satellites at other orbital positions, extra LNBs are required. That's why the newer DirecTV dishes have 3 LNBs, one for each orbital position. Along with the extra LNBs, the reflector itself is now elliptical in shape, 24 inches by 18 inches. This is to handle the signals arriving from the 18-degree satellite spread. Signals from the rightmost 119 position are reflected over to the left LNB, and signals from the left 101-degree position are reflected over to the right LNB. For DirecTV, the 3 transponder output of the 110 LNB is combined with the 11 transponder output of the 119 LNB to create a single output. An external or built-in switch is used to switch between the LNBs. It uses a 22 kHz tone generated in the receiver that's applied on top of the polarity voltage. Depending on the channel selected, the receiver knows which satellite to use. No tone defaults to the 101 degree LNB, while the presence of the tone selects the combined 110-119 degree LNB.
Newer Dish Pro antennas for the Dish network have 2 LNBs to receive the network's primary signals at 110 and 119 degrees. The LNBs and receivers operate differently than the ones we saw for DirecTV. They incorporate a European standard called Digital Satellite Equipment Control Protocol, or DISEC for short. See, it allows two-way signaling between the LNBs and the receivers. A voltage change is not used to select between odd and even channels. Instead, the LNBs output both even and odd channels at the same time on one cable by outputting odd channels between 950 and 1450 MHz and even channels between 1650 and 2150 MHz. Switching between LNBs, monitoring, and other control functions is done with the digital codes transmitted to the LNBs on a 22 kHz tone. To receive transponders at the 61.5 or 148 degree position requires a separate antenna. New Dish Pro technology switches can then be used to combine outputs from the 110 and 119 degree positions with the output from the 61.5 or 148 degree positions, allowing the user a single button channel change between all channels.
There are 2 approaches to installing multiple receivers in the same home. The obvious is simply to install a separate satellite dish antenna for every receiver. The other approach is to allow one antenna to be shared by multiple receivers. To do this typically requires a device called a multi-switch. Basically, a multi-switch allows every receiver to view any transponder channel on any satellite that the antenna can see. This requires a dual output LNB. The 2 independent outputs supply their left or right-hand polarized transponder channels at the same time. The basic multi-switch is placed between the dish and the receivers and gets its power from the DC voltage on the cable from the receivers. It fixes the voltage to each output of the dual LNB to fix the output channels. Depending on the polarity voltage it receives from each attached receiver, it switches the output to the receiver to the appropriate even or odd channels from the LNB. Multi-switches that support 2 or 3 LNBs use a 22 kHz tone from the receiver to select the appropriate LNB in addition to the polarity voltage.
This multi-switch receives the polarity voltage and tone from each receiver, and it switches the appropriate even and odd channel from the correct LNB to that receiver.
DirecTV multi-switches typically have 4 inputs, the left and right outputs from 2 LNBs, and 4 to 8 outputs for receivers. Multi-switches for Dish Network have 2 inputs for the dual LNB dish that supports both primary satellites, and an extra input for a secondary dish. This model supports 4 receivers, but is cascadable to support up to 12 receivers. Unfortunately, multi-switch and LNB designs are constantly evolving. Even the satellite and transponders change. So make sure and check that the LNB and multi-switch technologies you're using are compatible and recommended by the services you're using. Since multiple receiver installations are so popular, many manufacturers of multi-LNB dishes are building them with multi-switches built in. This 3 LNB DirecTV dish from Turk has a multi-switch built in which will support 4 receivers. This Dish Pro quad output dual LNB allows up to 4 Dish Pro compatible receivers to share the same LNBs. Due to the very high frequencies from the LNB to the receiver, and the fact that the receiver is supplying power to the LNBs over the coax, you need to be very careful not to exceed the installation specifications. Now, since it's passing the DC operating current to the LNB, about 200 mils per LNB, the DC characteristics of the coax cable is very important. Now, the maximum voltage drop from the receiver to the LNB should not exceed 1.25 volts. This works out to a maximum loop resistance of about 6 ohms. Now, we're using very good quality 18 gauge solid conductor RG6 that's been tested to over 2.2 gigs. more than adequate for a 150-foot cable run. Now, if you need to go longer distance, RG11 coax will really do the trick. Now, the signal level out of a LNB is expressed in dBms. Similar to dBmVs, only it's a unit of power rather than voltage. 0 dBm is a reference of 1 milliwatt. Now, typical signal levels out of an LNB are minus 35 dBm. That's sort of equivalent to plus 3 dBmV in a 75 ohm system. Therefore, the loss from the LNB to the receiver can't exceed 20 dB. This graph gives a maximum coax length for RG6 and RG11 at 1450 and 2250 MHz, allowing for a 5 dB loss margin. Now, we'll cover more of the installation issues in part 2 and 3 of this course.
Before you can design RF distribution systems, you need to have a good working knowledge of the components that go into these systems. We'll be using both active and passive components, such as amplifiers, splitters, and RF modulators, to be able to design these systems. Active components are so named because they're powered. We'll be looking at amplifiers, modulators, and demodulators. Amplifiers are required in almost all RF distribution systems, primarily to overcome signal losses in the system or weak source signals. While they come in all shapes and sizes, they are always drawn graphically as a triangle. The signal enters on the left and the amplified signal is on the right. The fundamental properties of amplifiers you will need to be familiar with are bandwidth, gain, noise figure, dynamic range, impedance, and maximum output. Gain is a measure of how much the amplifier amplifies and is always given in dB. A 10 dB amplifier will increase the input signal amplitude by 10 dB. Gains of 5 to 20 dB are typical for broadband RF amplifiers.
Amplifiers come in fixed gain models such as this, or variable gain models, where the gain is usually adjustable over a 10 to 20 dB range. A popular amplifier package for residential applications is this inline amplifier. These are usually fixed at 10 dB gain. It requires a companion inline power injector that places DC operating voltage on the coax center conductor. This can be handy when you need gain at a location that's far from a power source. Distribution amplifiers are often combined with splitters in one package, since the two are so commonly used together. One input is amplified to several outputs. We'll talk more about splitters shortly. Bandwidth defines the frequency range over which the amplifier will deliver its specified gain. For television RF amplifiers, this is usually 50 to 450 or 50 to 900 MHz. A real measure of the quality of an amplifier is how well it maintains its gain over its bandwidth. It should be within a few dB. This is a 0 dBmV broadband reference signal we'll use to demonstrate two amplifiers. The output of the first 10 dB amp is in fact 10 dB and flat over its specified 50 to 900 MHz bandwidth, while the output of the second 10 dB amp falls off dramatically above 200 MHz. An amplifier's noise figure is a measure of how much noise an amplifier adds to the signal it's amplifying. All components in an RF distribution system add a small amount of noise, but amplifiers are the noisiest. Noise figure is given in dB, and a smaller number is always better. The lower the noise figure, the smaller the input signal the amplifier is capable of using.
Since noise sources accumulate in a system, you want to keep the number of separate amplifiers in a system to a minimum. Remember, the carrier-to-noise level ratio should never be less than 40 dB. The dynamic range of an amplifier, or headroom as it's sometimes called, is a measure of the range of input signal amplitude that the amplifier will handle without distortion. The higher the better. A maximum input signal level of 30 dBmV is good. You will need to pay attention to this spec when doing RF system design to be certain that the input level into an amplifier does not exceed its input capabilities. This can be tricky when the source is an off-air antenna and the signal levels can reach as much as 30 to 40 dBmV. Any signal that overloads an amplifier will create a number of nasty intermodulation products, unwanted signals, spread over a wide frequency range. This can cause distortion on the channel being viewed as well as on other channels throughout the spectrum.
When selecting an amplifier for a distribution application, first select the gain you'll need. Remember, too much gain is worse than too little. If you need 10 dB, don't use a 20 dB amplifier. Make sure the bandwidth is adequate for the range of signals you need to handle. Check to make sure the maximum input signal level doesn't exceed the limits of the amplifier, and select the lowest noise figure that you can afford.
Modulators are like very small television stations that broadcast a baseband audio and video source onto a cable or off-air television channel. They have a baseband audio and video input and an F-connector RF output. You could hook the output of a modulator directly up to an off-air antenna and operate your own television station for your neighborhood. If no one complains, you might get away with it for a while, but remember, it is illegal.
Modulators come in a wide range of sizes, features, packaging, and number of inputs, from single-source single-channel to four-source four-channel models. All the modulators you'll be using are frequency agile. That is, you can select the output channel. You need to do this to set the modulator channel to a channel that's not used by local off-air or cable channels. Modulators typically use off-air channels when set at or below channel 69, and EIA standard cable channels when set above 69, although some can be set to IRC or HRC channel plans. As we saw earlier, a standard off-air or cable channel occupies a 6 MHz bandwidth. It's referred to as a vestigial sideband signal because it contains only the picture carrier and the upper sideband containing the chroma and audio. To save bandwidth, the other lower sideband has been removed. Now, to make modulators relatively inexpensive, they transmit both sidebands of a television picture, leaving out the expensive circuitry required to remove the lower sideband. This means they require a 12 MHz bandwidth, 6 MHz at the channel they're set to, and 6 MHz of the lower channel. Therefore, if you're using multiple modulators in a system, or combining modulator outputs with cable or off-air signals, you need to leave one unused channel between the selected modulator channels. So if a modulator is set for channel 80, for example, it will actually use channels 79 and 80. Modulator output levels are usually high, typically 25 to 35 dBmV. This comes in handy since they're usually placed in the internal path of a coax distribution system where losses are high before reaching a distribution amplifier. Newer modulators can support S-video as well as component video and stereo audio. They also provide a loop-through capability on the inputs. Modulators can also be built directly into camera modules. And new Dish Network satellite receivers are equipped with a frequency agile modulator for off-air channels 21 through 69. When selecting a modulator, make sure the output signal level is at least 25 dBmV, preferably adjustable. The frequency stability should be plus or minus 5 kHz or better, and the carrier-to-noise ratio should be 55 dB or better.
Next, we'll cover passive components. This includes attenuators, terminators, splitter combiners, diplexers, filters, and tilt compensators.
Let's start with attenuators. These are used to lower the amplitude of a signal. They typically come packaged in a barrel shape marked with a dB attenuation level. You'll find these commonly in 3, 6, and 10 dB versions. You can screw them together to achieve any amount of attenuation you need. They aren't made to dissipate any power, so they should not be used where there's a DC voltage on the cable, since they'll get hot and possibly burn out. Instead, you can insert a DC blocking capacitor between the DC source and the device. These will pass RF but block DC. These are also packaged in a barrel shape with F connectors on both ends. Screw-on terminators are used on any unused RF device input or output for two reasons: to prevent possible radiation of RF from the system, and to prevent any output signal from being reflected back to the source and causing possible signal distortion. They contain a 75 ohm resistor from the center conductor to ground. Make sure there's no DC voltage where they're used. You can also combine them with a DC blocking capacitor if necessary. They must be used on any unused outlet connector or unused output from an active or passive device. Grayfox makes a line of barrel connectors with built-in terminators. The blue end contains a 75 ohm resistor that's disconnected when a cable is screwed onto the connector. Next, let's cover splitter combiners. A splitter divides an input signal equally between two or more output ports. The ports are bidirectional and can be used to combine two or more signals as well. A splitter may or may not be DC passing. That is, it may pass a DC voltage, either for power or IR signals, over the coax. A voltage that appears on one port will appear on all other ports. Because they divide the signal level or power between the outputs. The outputs of a two-way splitter are typically 3.5 dB less than the input. The outputs of an 8-way splitter are typically 11 dB less than the input. Now the loss works both ways, so the output levels of a combined signals are also attenuated by the same amount. This chart shows the typical loss for a 2 through 16-way splitter combiner. Splitters also have a frequency range specification over which they operate. This can range from as little as 5 to 54 MHz to 5 to 1000 MHz. Carefully check the specs before buying. A coupler or tap is a special case of a splitter that divides the signal unevenly. The output through port has minimal loss, usually 1 dB, while the tap port has a high loss, usually from 9 up to 30 dB. Now the tap can be used in reverse to combine a very high signal with a low to normal signal. If it is not bidirectional, it's called a directional coupler. Taps are typically used to distribute cable signals in a tap rather than home run topology. And it's a very popular wiring technique for cable companies in single and multifamily homes.
Next, let's cover filters. Filters are a very common component in RF distribution systems. They're used to pass one range of frequencies while blocking another, and they come in 4 varieties: high pass, low pass, and band pass and band stop.
The low-pass filter is probably the most common. It passes frequencies below a frequency value and blocks frequencies above that value. Filters are either specified by their pass frequencies or by the pass channels. Real-life filters are not perfect. The attenuation increases gradually in the blocked part of the spectrum and reaches a maximum of -30 or 40 dB. Low-pass filters have a lower usable frequency limit as well. For example, this channel plus low-pass filter is rated to pass 40 to 600 MHz or cable channels 2 to 86. The attenuation slope is about 4 channels at 24 MHz, so the closest inserted channel should be 91 or above. A high-pass filter is just the opposite of a low-pass filter. It passes frequencies above a specified value and attenuates frequencies below.
A bandpass filter passes a range of frequencies in between a low and a high value. A band stop filter is the opposite of a band pass. It blocks a range of frequencies. Now these are also called notch filters and can be used to remove one or a group of frequencies or channels.
This channel plus notch filter is a good example. It blocks cable channels 64 to 70.
A diplexer is a combination of 2 filters in one package. They're used to combine or split 2 signal frequency ranges. The most common example is this satellite diplexer that'll combine the output from an off-air antenna up to 850 MHz with the output of an LNB between 900 and 1450 or 2150 MHz. This allows one cable to be used to carry both the satellite and antenna signals to a receiver location. A diplexer at the other end splits the signals back out for the TV and the satellite receiver.
A tilt compensator is typically used after an amplifier and before a long coaxial cable run to compensate for the attenuation of high frequencies in the cable. It simply provides an inverse attenuation, attenuating low frequencies more than high frequencies, just the opposite of the cable, assuming the typical loss you'd find in 200 feet of RG6.
The net result is an even signal at the wall outlet. They're also used to overcome uneven amplifier responses. Tilt compensators are often built into the output of distribution amplifiers. Check the output of your system before installing a tilt compensator to make sure it's needed. Cable companies routinely apply excessive tilt compensation before the drop to a home. The high cable channels above 50 are already at higher amplitudes.
Well, that wraps up part 1.
In part 2, we'll take all this knowledge that we've learned and apply it to the product planning stage.
Now, we've definitely learned a lot of material in this part, so take the time to review the material in your workbook before going on to part 2.